Let me remind you that last time we said that if I have a constant function c, the integral from a to b of the constant function c dx is given by c multiplied by the length of the interval, which is b minus a. And how do I know that that's the value of the integral? At this point, we don't know the fundamental theorem of calculus. And so at this point, how do I know this is the integral without knowing that? Well, I can just look at the Riemann sum. If I give you an arbitrary partition, okay, the Riemann sum will be this, right? The Riemann sum will be the sum I going from 1 up to n f of wi times delta xi, right? And what is f of wi in this case? The function f is a constant function, right? F is just x, right? Sorry, f of x is just c always. So what is f of wi? F of wi is just c. It's a constant function, right? So I get the sum I going from 1 up to n c times delta xi. And because the c is just a constant factor, I can take it outside of the sum. So I get c times the sum of delta xi. Am I clear? Now, what is delta xi? Delta xi is the length of the ith subinterval, right? So you're taking the sum of the lengths of the subintervals, right? So what's the sum of the lengths of the subintervals? The sum of the lengths of the subintervals will be the total length of the subinterval. Well, what's the total length of the subinterval? What's the total length of the interval from a to b? It's b minus a, right? If I am looking at the interval from a to b, what's the total length of that interval? B minus a. So remember, so that interval was divided into subintervals. So if I am summing up the lengths of the subintervals, I am getting the length of the entire interval, which is b minus a. So that's c times b minus a. So what is it telling me? It's telling me no matter what partition you pick, the Riemann sum is always equal to this quantity, c times b minus a. No matter what partition I pick, the Riemann sum is always equal to c times b minus a. Well, what's the limit as n goes to infinity? As n goes to infinity, the limit of the Riemann sum will be this quantity because it does not depend on n, right? The Riemann sum is always equal to this. Doesn't depend on n. Even if I take the limit as n goes to infinity, I'm going to end up with that. So that's how we know that the integral of this constant function is got to be c times b minus a. But you can also look at the picture. If c is a positive constant, then the graph is a horizontal line. So the integral from a to b of the constant function c is just the area of this rectangle. And the area of this rectangle is, of course, the length times the height, which is c. So c times b minus a. Okay? Everybody's okay with that? All right. And we talked about this. The integral from b to a is the same as the negative integral from a to b. Now here's another theorem. If I know that the integral from a to c and the integral from c to b exist, then I know that the integral from a to b will exist. And then integral from a to b is the same as the integral from a to c plus the integral from c to b. So I can break up the integral from a to b as the integral from a to c plus the integral from c to b. So notice that c, the upper limit here, upper limit of the first integral is the same as the lower limit of the second integral on the right hand side. Okay? So I can write the integral from a to b as integral from a to c plus the integral from c to b. Here c could be any number. As long as each of the integrals on the right hand side are defined, you could use that. Now c could be any number here. However, I can give you a good reasoning why this is true when c is between a and b. When c is between a and b, and let's say f is a positive function. For this equation to hold, f is not needed to be positive. But just to give you a justification using this picture, I'm going to use f is positive. And then c is in between a and b will be assumed. C doesn't have to be between a and b. C does not have to be between a and b. But if c is in between a and b, then it's easy to see why this is true. Well, notice if c is in between a and b, integral from a to c will represent what? Integral from a to c will represent the area below the graph of f above the interval from a to c. So this area will be represented by the integral from a to c. Integral from c to b will give you the area below the graph from c to b, right? When you add them up, you get the entire area below the graph of f from a to b, right? Which is what? Which is the integral from a to b. So the integral from a to b, the left-hand side of the equation gives you the area below the graph of f from a to b. The right-hand side, integral from a to c, gives you the area from a to c. C to b gives you the area from c to b. When you add them, you get the entire area. So this is a justification when c is between a and b, and f is not negative. But f is allowed to be negative, and c doesn't have to be between a and b. C could be bigger than b, c could be less than a. Still, that equation holds. How do you see that the other cases like that are justified? You can just make other pictures if you need to. But I'm not giving you a general, rigorous justification here. In any case, what you need to remember is this equation where the integral from a to b can be broken into two integrals. Integral from a to c, integral plus the integral from c to b. And a lot of the times it is useful. So just a quick example. If suppose you are given the integral from 0 to 10 of f, and you're also given the integral from 0 to 8 of f, then you know these two integrals. What's the integral from 8 to 10? How do I find that? Well, we just apply the previous theorem. Oops. Whoa. Alright, so what's the integral from 0 to 10? Integral from 0 to 10 is the integral from 0 to 8 plus the integral from 8 to 10, right? By the previous theorem. And then, what is known? I know integral from 0 to 8. I know the integral from 0 to 10. All I have to do is plug those numbers and solve for integral from 8 to 10. And integral from 0 to 8 was what? 12. Integral from 0 to 10 was 17, and you just get the answer. Okay. So the integral from 8 to 10 is just 5. Is everybody okay with that? Back up a little bit. A little bit more, or this is fine? Okay. There are two comparison properties. If the number one number one in this theorem tells you, if you know that the integrand is non-negative, integrand function is non-negative for any x between a and b, then the integral has to be non-negative. So the value of the integral is non-negative if you know that the integrand is non-negative. Okay. Number two says, if the function f is larger than the function g for any x between a and b, then you know that the integral of f must be bigger than the integral of g. Okay? Now, in number two, we are not assuming that f and g are non-negative. It's important to understand that number two, we are not assuming f and g are non-negative. They may have negative values. But we are assuming that f is always bigger than g. So that means in terms of the graphs, the graph of f is above the graph of g. Right? Then we can say number two holds. Everybody is clear on these two? All right. And we can justify both of these properties by using Riemann sums and stuff, or graphs, intuitive argument. But I think it's pretty clear why they should hold. Okay. I mean, if you think about it, if f is bigger than g, then every Riemann sum will be bigger than the corresponding Riemann sum of g, right? So there is nothing special going on there. All right. 4.3. This is where we talk about the fundamental theorems of calculus. Okay, so let's say I have a function f, and the function f is continuous from a to b. Okay, it's a continuous function from a to b. Okay, and I want to define a new function, and I'm defining a new function g of x. Now, if I want to define a function, if I want to specify a function to you, what do I have to tell you? I have to tell you what the function does to an input. In other words, how does the function computes the output? I have to tell you that recipe, right? So what I'm telling you here is that the value of the new function g is given by the following. G of x, if x is the input, then the output is given by the value of this integral. So integral from a to x, f of t dt. So I am integrating the function f over the interval from a to x. Whatever that value is, that's the value of this function. Okay? And I am defining this new function g for any x between a and b. So what's the domain of g? Domain of g is a to b. Okay, I'm defining g for x between a and b. Looks like a very weird function, right? At first look. But this is not really that weird. Let's look at an example. Let's say I have the function g of x, and then the function g of x is the integral from 0 to x 2 dt, right? The integral, the value of the function g at x is given by the integral from 0 to x of 2 dt. Do I know the value of this integral? Well, this is just a constant, right? And I know exactly how to find the integral of a constant function. What is that? The integral of a constant function is basically what? The constant multiplied by the length of the interval over which you're integrating, right? So it will be 2 times x minus 0, which is exactly the function 2x, right? So the function g of x, which I defined as the value of this integral, is in fact the function 2x, our familiar function 2x in disguise, right? So I just wrote the function 2x in a different way, right? Is everybody okay with that? let's look at another example. It's not the other things are not so important. If I have the integral from, if I have the function g of x defined by the integral from 0 to x t dt, what's the value of that function at x? Well, what the integrand here is t, right? So what's the graph of this integrand? Well, the graph of this integrand is the same as the graph of the equation y equals to t, right? So I have the t-axis, I have the y-axis, and my integrand is t. So what's the graph of that? Well, the graph of that is just a straight line at 45-degree angle, right? You agree with that? The graph of this integrand is exactly this line. Does that make it? Are you okay with that? So this is a function of t, right? So y is t, right? And so now I am integrating from 0 to x. So 0 to x. So the integral from 0 to x will be will give me what? The area below the graph above the interval from 0 to x, right? What area do I have? I have a triangle here. If this number is x on the t-axis, then what's the height of the graph? The height of the graph will be x as well, because this is the function y equals to t. So it means that the input and output are the same, right? That's the function. Input and output are the same. So then, what is the area? Well, the area is half times base times height. Well, half times base times height, that's half of x squared. So once again, I have the function 0 to x t dt. That's exactly the function half of x squared. Okay. In my picture, I assumed x is positive, but even if x is negative, the same formula works. Okay. So generally speaking, remember, given the function lowercase f, we assume the lowercase f function is a continuous function. We are defining the function g, which is given by the integral from a to x f of t dt. Let's assume f is a non-negative function. If f is a non-negative function, I can give you a geometric interpretation of the function g. If f is not a non-negative function, then the picture becomes more complicated. But f is non-negative, then the graph of f will be above x-axis, and I am looking at the graph of f between a and b. And then, if I pick any x between a and b, what's the integral from a to x? The integral from a to x of f of t would be the area below the graph of f, above the interval from a to x, which is this area here, right? The pink, the area that I labeled by using the pink color, that's the value of g of x, right? G of x is exactly the area, or maybe I try to use that color. So this area here is the value of g of x, right? You guys agree with that? All right. One more example. Let's say g of x is the integral from -1 up to x, square root of 1 minus t squared dt. And I am defining this function g of x for any x between -1 and 1. Okay? So the domain of g of x is -1 to 1. That's the domain of g of x. Now let's see what this function is. I cannot tell you at this point the closed form value of g of x. That is, Remember, in my previous examples, I said g of x was, in my first example, was just the function, what? What was that? In the first example, the function g of x turned out to be 2x. In the second example, the function g of x turned out to be half of x squared. In this example, I can't tell you that. Okay. However, I can't tell you that right now, but if we know a little bit more, I could have told you what this function g is as an algebraic expression in terms of x or in terms of familiar other familiar functions. But at this point, I just want to know what is g of 0 or what is g of 1. Okay, so let's see. Let's look at the integrand. Integrand is the root of 1 minus t squared. So the integrand function is y is root of 1 minus t squared, right? So if t is the input, then the output y is given by the square root of this quantity. Right? That's the function. What is the graph of this function? Well, let's square both sides. If I square both sides, I'm going to get y squared is 1 minus t squared. And then if I can rewrite that as y squared plus t squared is equal to 1. In the y-t-axis, what's the graph of that equation? It's a unit circle. Right? What's the graph of x squared plus y squared equals to 1? It's the unit circle. Instead of using x, I'm using t, right? So in the y-t-axis, the graph of this equation is the unique circle. But then, what's the graph of my integrand? The graph of my integrand is actually only the upper half of the circle. Only the upper half of the circle. If I take y to the negative root of 1 minus t squared, then I get the lower half of the circle. Okay? Now, so I know that the yellow curve, that's the graph of my integrand. Now, someone tell me what is the value of g of 0? What's the value of g of 0? The value of g of 0 is what? G of 0 would be negative 1 to 0 square root of 1 minus t squared dt, right? And how do I know that that value is this? Well, when you integrate from negative 1 up to 0, when you integrate from negative 1 up to 0, what is that? Well, that's the area below the graph of the integrand above the interval from negative 1 to 0. Well, that area is 1/4, right? 1/4 of the entire circle. So the area that I highlighted with blue color here, that's exactly 1/4 of the area of the entire circle. Right? So g of 0 is 1/4 of pi. Can you tell me what is g of 1? What is g of 1? Yeah, it's the upper half of the circle, right? If I go from negative 1 up to 1, I'm looking at the area below the graph of the upper half of the circle, right? That's exactly half of the circle. So that will be half of pi. Pi is the area of the entire circle, right? Because the radius is 1. So pi r squared is the area. Because r is 1, the entire area is pi.
So like it takes 2 pi to go around the whole circle.
Yes.
Only pi, like the whole area of the whole circle.
The area of the, okay, so if you have a circle of radius, r, right? What's the area? What's the area formula? Pi r squared. So then, if the radius is 1, the area becomes pi. Okay. All right. So now the fundamental theorem of calculus part 1. Okay, fundamental theorem of calculus part 1. I am usually going to refer to it as FTC1. What is it telling us? Once again, the assumption is f is continuous from a to b. I am defining a new function g of x. The value of g of x is the integral from a to x, f of t dt. X is between a and b. So my assumption is f is continuous, and I am defining a new function, and I am making a conclusion about the new function g. What is the conclusion? The conclusion is that the function g is also continuous. Not only that, I know the derivative of the new function. The derivative of the new function at x is the same as the integrand at x. Okay? The derivative of the new function at x is the same as the integrand at x. What I actually did, when we defined this new function g, what we actually did is that we wrote down an antiderivative of the integrand function, right? G prime of x is f of x. So g is the antiderivative of f. So this new function, g of x, which is defined by the integral from a to x, f of t dt, that's exactly a antiderivative of the integrand. That's what is expressed here. G is the antiderivative of f. Am I making sense? G prime of x is f of x. Essentially, we came up with an antiderivative of the integrand, which shouldn't be surprising given the fact that we are after all integrating f to come up with the value of g. Okay, so g is the antiderivative of f. Let's do an exercise. Let's say I have the function g of x, which is the integral from 0 to x square root of 1 plus t squared dt. What's the derivative? What's the derivative? Square root of 1 plus x squared. Very good. So basically the derivative is by FTC1 integrand evaluated at x, right? You guys agree with that? Okay. How about this example where I have capital F of x is the integral from x to 0 square root of 1 plus t squared dt. What would be the derivative now? What would be f prime of x? Yeah. Before you can apply FTC1, remember in FTC1 in FTC1 the lower limit is a fixed number a, the upper limit is x. And then we are saying g prime of x is f of x. G prime of x is the integrand evaluated at the upper limit. And so here, before I can apply FTC1, I have to switch the limits of integration because I want a constant fixed number as the lower limit, and the upper limit would be the variable, and then or the input of the function, and then this would be this. And now I could say that the derivative would be negative by FTC1. It's the integrand evaluated at the upper limit. And that's the derivative. Is everybody okay with that? Questions? Okay, while we are at it, let's do one more example on this, and then we're going to go to FTC2. Okay, how would you find the derivative of capital F prime of x here? Capital F of x is the integral from x to the 4 to 1 of secant t dt, right? So how would I find this derivative? Obviously, it has to do with FTC1, right? But remember, in FTC1, before I apply it, I have to make sure that the lower limit is what? Lower limit is fixed. So I should be switching. I should be switching the. Yes, I should be switching. Yeah, I need to introduce a negative sign, and so I am switching the limits of integration so that I have the lower limit fixed. Now, can I apply FTC1 now? In FTC1, the upper limit was just x. It wasn't a function of x like x to the 4 or sine x or something else. So how would I find the derivative when I don't have just x? Okay. So what should I do? Well, what you need to realize is that if I look at this function here, that function I claim is the composition of two functions. This integral function that I have is the composition of two functions. What are they? Well, the outside function is the integral from 1 up to x secant t dt, and the inside function is just x to the 4. You agree with that? I am claiming that the integral function that I have 1 up to x to the 4, that's the composition of the integral function 1 up to x, and then the inside is x to the 4. If you want to verify that, well, let's look at f of g of x. What is f of g of x? Well, this is f of x to the 4. And then what is f of x to the 4? How do you find f of x to the 4 if you know f of x? If you know f of x, you replace x by x to the 4, right? So if you replace x by x to the 4 in f of x, right? So this is f of x. This thing here is f of x. And if I replace x by x to the 4, I get 1 up to x to the 4 secant t dt, right? Which is exactly the same as the function that I said was the composition of two functions, right? Am I making sense? Because the function that I have is a composition, I have to apply the chain rule. I have to apply the chain rule to find the derivative. So how would you apply the chain rule? What's the derivative of this by using the chain rule? Uh-huh. 4x cubed, very good. So if you look at the what's the derivative of the outside function? The outside is lowercase f. If I look at the lowercase f, what's the derivative of lowercase f? By FTC1, the derivative of lowercase f is what? Secant x. But in chain rule, what do we do? If I take the derivative of f of g of x, by chain rule, the derivative is f prime of g of x times g prime of x, right? Which is the same as f prime of x to the 4 times g prime of x. Now, what is f prime? F prime is just secant of x, right? But then I have to evaluate f prime at x to the 4, so this will be x to the 4, and then g prime was just 4x cubed, because g of x is x to the 4. So that should be the derivative. Okay? You don't have to write all this down. I'm just showing you why chain rule is applied here. But usually what I tell you when I apply chain rule is the following. You are trying to find the derivative of the function integral from 1 up to x to the 4 secant t dt. You look at the integral from 1 up to x to the 4, and you wish that x to the 4 is just x. If x to the 4 is just x, you know the derivative by FTC1. So if so let me say this. So capital F prime of x, if x to the 4 were just x, then I know by FTC1 the derivative would be the integrand evaluated at the upper limit, right? FTC1 says the derivative would be integrand evaluated at the upper limit, given that the upper limit is just x. But the upper limit is not just x. You have to multiply by the derivative of that, right? But essentially what you're doing though is you're applying the chain rule. Okay? Oh yes, I had a negative in front there. Yes, thank you. Is everybody okay? All right. You can think about this when you go home, and if you have any more questions, let me know. But I won't do any more examples of that. Let's go to FTC2. FTC2. Once again, we are assuming that lowercase f is a continuous function on the interval from a to b. And let's say capital F is any antiderivative of lowercase f. So capital F is some antiderivative of lowercase f. Then what's the integral from a to b of f of x dx? What's the integral from a to b of f of x dx? Well, that integral is given by the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit, right? So what's the definite integral from a to b of f of x dx? Well, just the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. And I'm going to use this notation, f of x within brackets and then b and a. I'm going to use that notation to denote that difference, f of b minus f of a. So f of b minus f of a will be denoted by f of x within brackets b superscript b and subscript a. Okay. All right. So let's see how that is applied. I mean, if you didn't have this theorem, well, life would be much more difficult in order to compute many of the integrals, right? So, what's the integral from 0 to 1 of x squared? Well, by FTC2, what do I have to do? All I have to do is find an antiderivative. What's an antiderivative of x squared? X to the 3 divided by 3, right? That's one antiderivative of x squared. And then you evaluate the antiderivative at 1 minus the antiderivative evaluated at the at 0, right? And what do you get? 1/3. Right? Antiderivative at the upper limit minus the antiderivative at the lower limit. All right, so let's look at a little bit more complicated example, but I'm pretty sure it's pretty easy at this point for you. Integral from 0 to 4, x squared minus 8x dx. What should I do? Well, I want to find an antiderivative. What's the antiderivative of x squared once again? X cubed over 3 minus, what's the antiderivative of 8x? 8x squared divided by 2, right? And then 0 to 4. Just do a little bit of a simplification there. So 8x squared over 2 is the same as 4x squared. And then now you want to evaluate the antiderivative at 4. Evaluate the antiderivative at 0. Subtract. Whatever you get, that's the result, right? That's the value of the integral. Are we okay with that? Of course, we have to be able to use the U-Substitution to find definite integrals. I have already reviewed how to use U-Substitution to find antiderivatives. Let's look at what we should do to find definite integrals. Oh, by the way, before I move on, can someone tell me why integral from 0 to pi over 2 cosine x dx, antiderivative of cosine is sine, pi over 2 0, evaluate pi over 2, evaluate at 0, subtract, you're going to get 1. What's the, if you look at the integral from negative 1 up to 3, 1 over x squared dx, I'm telling you, you cannot apply FTC2 in order to find that integral. Why? Yes, you better make sure, before you apply FTC2, you have to make sure the integrand is continuous over the interval from A to B. You have to make sure that the integrand is continuous over the interval where you're taking the integral, right? So in this case, my integrand is discontinuous at 0, and 0 is inside here, right? However, if I integrate from 1 up to 3, right, can I apply FTC2? If I go from 1 up to 3, I can. But if I go from negative 1 up to 3, I cannot, right? Because then my function integrand becomes discontinuous at certain point in that interval. You can't apply it. Is everybody okay? Also, one thing you want to realize is that, remember when I defined the definite integral, I said the definite integral exists. If the definite integral exists, then the integrand has to be a bounded function, right? If the definite integral exists, then the integrand has to be a bounded function. If you look at the integrand here, it's not bounded in that interval. Why? Because at 0 you have an asymptote. So it's not a bounded function. Okay? Even that tells me that this integral doesn't exist. Right? This integral doesn't exist. All right. One thing you want to remember, integral from a to b, f prime of x dx is the same as f of b minus f of a, right? Because my integrand is f prime, right? What's the antiderivative of f prime? Antiderivative of f prime is f. So once again, by FTC2, the integral is the antiderivative at b minus the antiderivative at a, right? Why did I write it in this way? Well, what is the meaning of f prime for a function f? F prime is the rate of f, right? F prime is giving you the rate of change of f. So this equation is telling you, if you integrate the rate of a function, you end up with the net change of the function. If you integrate the rate of the function f from a to b, you end up with the net change of the function from a to b. Am I making sense? For example, if the function f is the velocity function, what is velocity? Velocity is the rate of change of position function, right? Rate of the position. So if you integrate the velocity, you end up with the net change of position, which is the net displacement, right? So you need to remember this, because a lot of the times in applications like in physics or some other courses, you might see these interpretations playing out. Okay? Alright, now the substitution rule for definite integrals. What's the substitution rule for the definite integral? If I have the integral from a to b of f of g of x times g prime of x dx, so what does it mean? My integrand has two factors. My integrand has two factors. So one factor is f of g of x, the other factor is g prime of x, right? One factor is the composition, the other factor is the derivative of the inside of that composition. If I have something like this in my integrand, then I can simplify that by doing the following. I can write this integral as the integral of f of u du, where the limits of integration now will be g of a and g of b. How am I going from left to right? How am I going from left to right? Well, I am picking u to be g, and I am picking g prime of x dx to be what? Du, right? So if you take u to be g of x, then du would be g prime of x dx. And if you make that substitution, you end up with the integrand f of u, right? So this guy becomes du here, right? And g of x becomes u. And how am I changing the limits of integration? Well, if x is a, what is u? If x is a, u is g of a. If x is b, u is g of b, right? So that's why I'm getting the limits of integration. Okay? So if I have the integral from a to b of f of g of x, g prime of x dx, I can rewrite that as the integral of f of u du, where u goes from g of a to g of b. Okay? All right. Let me take one more minute to just finish it up, and I'll give you 5 minutes. I'll finish 5 minutes early tomorrow. Okay? Is that okay? All right. So integral from 0 to 1, 1 minus x to the 50. Integral from 0 to 1, 1 minus x to the 50. How would I do this problem? Well, you look at 1 minus x to the 50. I gave you the general formula for the substitution. Usually, you don't have to think about it. Just look at 1 minus x to the 50. You wish 1 minus x was just x, because if it were just x, then you have x to the 50, and you can apply the power rule. It's not x, so I'm going to make the substitution u equals to 1 minus x. If I make the substitution u equals to 1 minus x, then what is du? Then du would be negative dx. If du is negative dx, then what is negative du? Negative du would be dx. Well, then I make the substitution. Integral of 1 minus x to the 50 would be 1 minus x will become u, and then dx will become negative du, right? What would be the limits of integration? Now remember, x is going from what to what? X is going from 0 to 1. When x is 0, what is u? When x is 0, u is 1. When x is 1, u is 0. So u goes from 1 up to 0. Okay, so I get 1 up to 0. And then what is the antiderivative here? The antiderivative is u to the 51 over 51. The limits are 0 and 1. Actually, let me erase those c. I don't need those c here, sorry. I don't need this here either. I was trying to find the antiderivative there, sorry. So this is, now what do I do? Well, I just plug in 0 and 1, right? You plug in 0, you plug in 1, you subtract. At the end, what you're going to get is 1 over 51. Okay? Again, I did this problem very quickly. It's not. We are going to do more substitution problems tomorrow, but they will relate to the new material of the course. Okay? All right. So I'll see you guys tomorrow. So from tomorrow, we start the new material from Calc2.